Hello students, welcome back to Sir Rasayan. Today I am going to start class 11 organic chemistry. Berzelius, a Swedish chemist, proposed that the organic compounds can't be prepared in the laboratory because some mysterious force is responsible for their formation. This mysterious force was called vital force. And the underlying theory was called vital force theory. In short, VFT. But in 1828, a German chemist F. Wohler prepared an organic compound, urea, from an inorganic compound, ammonium cyanate. This is ammonium cyanate. Heating symbol. This is urea. Some rearrangement of atoms gives the product here. So, urea was the first organic compound which was prepared in the laboratory. In 1845, Kolb synthesized acetic acid. Acetic acid is CH3COOH. And Berthelot in 1856 synthesized methane. So, formation of these organic compounds showed that organic compounds could be synthesized in a laboratory. Nowadays, most of the organic compounds are prepared in the laboratory. Next, we should know what is organic chemistry. It was observed that almost all the organic compounds contain both carbon and hydrogen atoms, and some of them also contain the atoms of some other elements like nitrogen, oxygen, phosphorus, halogen, etc. Carbon and hydrogen containing compounds are called hydrocarbon. In hydrocarbon, only carbon and hydrogen are present. So, what should be the definition of organic chemistry? The hydrocarbon and their derivatives are called organic compounds, and the branch of chemistry which deals with the study of those compounds are called organic chemistry. Now we should know why it is important to study organic chemistry. Organic compounds are very useful in our everyday life. Our clothes, shoes, cosmetics, medicine, dyes, paints, etc. contain organic compounds. So we need to study about them. Complex molecules like deoxyribonucleic acid means DNA, and proteins, carbohydrates, all are organic compounds. So we have to study about them in detail. Now see, carbon is the main element present in organic compounds. Therefore, we should know about characteristics of carbon atoms. So first one is tetravalency of carbon. Carbon is tetravalent. So what is that? You know, atomic number Z of carbon is 6. So its electronic configuration will be 1s2, 2s2, 2p2. This is valence shell. Now in ground state, valence shell electrons are distributed how? 2s electrons are there and 2p electrons are there. So here 2s electrons are there like this, paired, and 2 unpaired electrons are there. But in first excited state, this is 2s, 2p. One electron will move from 2s to 2p. So now distribution will be, electronic distribution will be like this. So here number of unpaired electrons are 4. These 4 orbitals with 1 electron each available for covalent bond formation. That's why covalency of carbon here is, from excited state, it is 4. Because number of unpaired electrons are 4. Here covalency in the ground state is 2. Next point, carbon atom can form multiple bonds. Like this is double bond, or this is triple bond. Everywhere you have to take care about the valency of carbon. See, 1, 2, 3, 4 means 4 covalent bonds should be there. 1, 2, 3, 4. Here 1, 2, 3, 4. For this carbon also 1, 2, 3, 4. Next point, tetrahedral shape. As for example, methane. This is methane. Methane molecule is tetrahedral in shape. 4 covalent bonds are along the 4 corners of a regular tetrahedron for tetrahedral shape, and here bond angle is 109 degree 28 minutes. See here 4 covalent, this is central carbon atom, consider methane, and here 4 covalent bonds are there. So 4 covalent bonds are along the 4 corners of a regular tetrahedron. Just imagine about a tetrahedron, and then you can consider if it is methane, here, here, here and here at the 4 corner of the tetrahedron 4 hydrogen atoms are there, and central atom is carbon, and here bond angle between 2 bonds, between these 2 bonds, these 2 bonds, or these 2 bonds, or these 2 bonds, these 2 bonds, these 2 bonds, angle is 109 degree 28 minute. Next point, a large number of organic compounds exist due to self-linking property of carbon. Carbon is having self-linking property, and this is called catenation. Catenation. Due to this property, we are getting large number of carbon compounds. So you can write, note down, due to this property of carbon, we get a large number of straight chain, branch chain, and closed chain straight chain, branch chain, closed chain, covalent compounds. In all these compounds, carbon is tetravalent. So, self-linking property of carbon gives this type of straight chain arrangement. See here, no branching is there. Okay. And this is branch chain arrangement. So, what is branch chain arrangement? Means this is main chain. From this chain, one branching is there. Here, two branching are there. Okay. And closed chain arrangement is also possible. Here see cyclic structure. This is 3-membered ring, this is 4-membered ring, and this is 5-membered ring. Like that way 6-membered ring, etc. are possible. Now see, in chemical bonding chapter you have studied hybridization. What is hybridization? It is the process of mixing up of orbitals of the same atom of slightly different energies and resulting the formation of new set of orbitals of equivalent energies. Now see, if your compound, if your carbon is having this type of structure, means it is having 4 sigma bonds and no pi bonds, hybridization of the carbon is sp3. And here bond angle is 109 degree 28 minute and shape of the molecule is tetrahedral. If carbon is having 3 sigma bonds and 1 pi bond, see, between two atoms, first bond is sigma bond and next bond is pi bond. So here 3 sigma bonds are there and 1 pi bond. Hybridization of the carbon is sp2. Here ideal bond angle is 120 degree and shape of the molecule is trigonal planar. If carbon is having this type of structure, means 2 sigma bonds and 2 pi bonds, hybridization of the carbon is sp and here bond angle is 180 degree and shape of the molecule is linear. Now see, hybridization influences the bond length and bond strength in organic compounds. Now see, sp3, sp2, sp. Here percentage S character. For sp hybridized orbital, it is 50%. Here out of 3 orbitals, 1 is S. So, this is 33.33%. And here out of 4 orbitals, 1 is S. So, it is 25%. For sp, sp2 and sp3 hybridized orbital, percentage S character is 50%, 33.33% and 25% respectively. sp hybrid orbital contains more S character and so it is closer to the nucleus and forms shorter bond. And shorter bond means stronger bond than sp3 hybrid orbital. So, what is the relationship between bond length and bond strength? They are inversely proportional. Bond length is inversely proportional to bond strength. That means if bond length is small, bond is very strong. Is it clear? sp2 hybridized orbital is intermediate in S character between sp and sp3. So the bond length and bond strength of the double bond is intermediate between bond length and strength of single and triple bond. Now for carbon-carbon single bond, bond length is 1.54 angstrom. For carbon-carbon double bond, bond length is 1.34 angstrom. And for carbon-carbon triple bond length is 1.20 angstrom. Since bond length is inversely proportional to bond strength, so therefore carbon-carbon triple bond, since it is having lesser bond length, it is strongest bond between carbon-carbon single bond, carbon-carbon double bond and carbon-carbon triple bond. It will form strongest bond. Clear? The greater the S character of the hybridized orbital, the greater is the electronegativity. So electronegativity order of the carbon atom will be like this. sp hybridized orbital is most electronegative, then sp2, then sp3, because sp hybridized orbital is having 50% s character. This is having 33.33% and this is having least 25%. Now we will study some characteristic features of pi bonds. To understand the first point, we should know about two types of overlapping. One is axial or head-on overlapping. When two p orbitals overlap along the internuclear axis, that is called axial or head-on overlapping. See, two p orbitals are there. This is internuclear axis. So here, see here, overlapping of the two p orbital is taking place like that way. Okay, so that is called axial or head-on overlapping. Due to such type of overlapping, sigma bond is forming. For lateral or sideway overlapping, two p orbitals will be like that. Orientations of the two p orbitals will be like that, and overlapping will take place here and here, and we will get pi bond. Now see, first point is here, for pi bond formation, parallel orientation of the two p orbitals on adjacent atoms is necessary. So this is parallel orientation. Parallel orientations, it is like that. Okay, parallel orientations of the two p orbitals on adjacent atoms, it is like that, or you can see like that way. Parallel orientation. Okay, it is forming pi bond. Parallel orientation is necessary for what? For proper sidewise or lateral overlapping. Next point, to make parallel orientations of the p orbital in, this is ethene, C2H4, ethene. All the atoms must be in the same plane. If all the atoms, means all the atoms involved here for double bond formation, if they are not in the same plane, then parallel orientations, means these parallel orientations of the p orbitals will not be maintained. Next point, both the p orbitals are perpendicular to the plane of the molecule. Means if this is molecular plane, then both the p orbitals will be like that, perpendicular to the plane of the molecule. Then only here and here overlapping of the orbital will take place. Means here and here overlapping of the orbital will take place. Next point, rotation about carbon-carbon double bond is restricted, because rotation of one CH2 group, see here, rotation of one CH2 group with respect to other, means if you fix one CH2 group and if you want to rotate another CH2 group, so rotation of one CH2 group with respect to other prevents maximum overlap of the p orbitals. Therefore, rotation about carbon-carbon double bond is restricted. Now see, this is ethene molecule. Ethene means C2H4. This is structure, CH2 double bond CH2. So ethene is having one sigma bond and one pi bond. This is orbital picture of ethene showing formation of pi bond, and this is showing pi electron cloud. Now see here, lateral or sideway overlap is taking place between p orbitals of adjacent carbon atoms. These two are adjacent carbon atoms. See, overlapping is taking place here and here, since it is lateral overlap. So, you can see pi electron cloud is here and here, only above and below the plane of the molecule. Now see, if you point, since the electron cloud of the pi bond is located above and below the plane of the bonding atom, so electrons of the pi bonds are easily available to the attacking reagent. They are loosely bound, okay. So in molecules having multiple bonds, these pi bonds are most reactive centers. Now you can think this in another way. For sigma bond, there is greater extent of overlap. Two p orbitals are there. Here, axial or head-on overlapping is taking place between two p orbitals and sigma bond is forming. So here greater extent of overlapping is taking place. But for pi bond formation, here there is lesser extent of overlap. And remember one thing, strength of covalent bond is proportional to extent of overlap. Since extent of overlap is greater in sigma bond, therefore sigma bond is stronger than pi bond. Strength. Sigma bond is stronger than pi bond. Therefore pi bonds are more reactive. Now see here, some problem we will solve. How many sigma and pi bonds are present in each of the following molecules? Number 1, this molecule is given. So three things you have to remember. First, write complete structure of the molecule showing all bonds. So complete structure of this molecule we can write like that way. 3 hydrogens are there. So like this. Now this carbon is bonded with this C. Here one hydrogen is there. Next double bond. This C, then H, CHO group. After that, everywhere valency of atoms you have to check. Valency of atoms should be satisfied. So carbon is tetravalent. So you check 1, 2, 3, 4. Tetravalence is satisfied. Here also 1, 2, 3, 4. For this carbon 1, 2, 3, 4. For this carbon 1, 2, 3, 4. So it is satisfied. Now you remember between two atoms, first bond is sigma and other bonds are pi bonds. So between this carbon and this carbon, first bond is sigma bond and next bond is pi bond. Now how many CH sigma bonds are present? How many CC sigma bonds are present? How many CO sigma bond is present? Now CC pi bond and CO pi bond. Now 1, 2, 3, 4, 5, 6. So 6 CH sigma bonds. Now CC sigma bonds 1, 2, 3. CO sigma bond 1. Because here one is sigma, another is pi. CC pi bond 1, CO pi bond 1. Done. Next problem. This is next molecule. So first what we have to do, we have to write complete structure showing all bonds. Then you see all valencies are satisfied or not. Done. Now you see between two atoms, first bond is sigma bond, another bond is pi bond. So here how many CH sigma bonds are there? 1, 2, 3, 4, 5, 6. How many CC sigma bonds are there? 1, 2, 3. How many pi bonds are there? CC pi bonds? 1, 2. Hope it's clear to you. Next molecule is this one. I am writing its complete structure. CH2 means this one. Double bond CH, then CN. C triple bond N. Now you have to find out sigma and pi bonds. Done. This is your practice question. You just do it. Here CH sigma bonds are there, CC sigma bonds are there, CC pi bonds are there, CN sigma bonds are there, and CN pi bonds are there. Done. So here number of CN pi bonds, CN. How many? First one is sigma and pi bonds are 2. Others you do it. Next problem, find out the type of hybridization of each carbon atom in the following compounds. First one is this one. So you have to write complete structure. CH3 with carbon, 3 hydrogens are attached, and here one bromine is attached. So it is having, this carbon is having 4 sigma bonds. That means this carbon is sp3 hybridized. Next one is HCOOH. So here how many? 3 sigma bonds are there, 1 pi bond is there. Therefore, it is, this carbon is sp2 hybridized. Next structure, CH3 CO and H2. For this carbon, 4 sigma bonds are there. So this carbon is sp3 hybridized. For this carbon, 3 sigma bonds are there, 1 pi bond is there. So it is sp2 hybridized. Next example, you write the complete structure here. CN means this one. After that you see here 4 sigma bonds are there. So this is sp3 hybridized. This carbon, here also 4 sigma bonds are there. This is sp3 hybridized. And here 2 sigma bonds are there, 2 pi bonds are there. So this carbon is sp hybridized. Done. Last another molecule I am giving. CH2 double bond C double bond O. So you have to write like that way. So here 3 sigma bonds, 1 pi bond. This is sp2 hybridized. And here 2 sigma bonds, 2 pi bonds. That means this carbon is sp hybridized. Done. So today till this. Thank you for watching.